Welcome back to GCSE Science Simplified. Today, we're tackling something that can feel tricky at first, the motor effect. Don't worry, by the end of this episode, you'll not only understand it, you'll be able to explain why electric motors spin, why maglev trains float, and how tiny forces on wires produce real motion. It's one of those ideas where what's invisible is actually doing all the work. Imagine a straight wire carrying an electric current. Now, bring a magnet close to it. Something remarkable happens. The wire feels a push or a pull. At the same time, the magnet feels an equal and opposite push. This is a real-life example of Newton's third law in action. But the push doesn't come from anything touching. The force comes from the interaction between magnetic fields. It's like two invisible dancers, each one moving because of the other's presence. So how does this force appear? The answer is magnetic field interactions. The current in the wire generates its own magnetic field. The magnet already has a field. Where these fields meet, they interact. The overlapping fields push or pull on each other. Think of it like two gusts of wind meeting. The way they combine can push leaves in different directions. The same happens with magnetic fields, except you can't see it without iron filings or plotting compasses. Here's a tool that makes predicting the direction of motion much easier. Fleming's left-hand rule. Stretch out your left hand like this. Oh, wait, it's a podcast. You can't see me. Your first finger or your forefinger, point it straight forward. This is the direction of the magnetic field, going from north to south. Your middle finger points in the direction of the current. This needs to be held at 90 degrees to your forefinger. And then finally, with your thumb pointing straight up, we have the direction of the force, or the motion that it will move. This is exactly how engineers know which way a motor's coil will spin before they even turn on the power. Imagine your hand as a tiny control panel telling you which way the invisible forces will push. It's a neat physical model for something that's otherwise invisible. Physics isn't just about ideas, it's also about numbers. The force on a conductor in a magnetic field is calculated using this equation. Force, measured in newtons, equals the magnetic flux density, measured in teslas, multiplied by the current, in amps, finally multiplied by the length of wire in meters. This means if we increase the current, the force increases. Increase the length of the wire, the force increases. And guess what? Using a stronger magnet means a stronger force. It's simple multiplication, but it describes the invisible push we just modelled with Fleming's left-hand rule. Now let's see how this produces rotation. In an electric motor, a wire loop sits in a magnetic field. Current flows through the loop. One side of the loop is pushed up, the other side is pushed down. Here's the tricky bit. If the loop kept spinning past halfway without any adjustment, the forces would start to oppose the rotation and cancel out, therefore no motion. Here's a model that makes it easy to picture. Imagine a roundabout at a playground. You push from one side and it spins in the right direction. You don't follow the roundabout round, you just wait and keep pushing that side in the same direction. If you didn't push it at the right timing, or if you swapped to the other side of the roundabout and then pushed against the roundabout, it would stop. The commutator in a motor acts like you moving to the other side at exactly the right moment. It reverses the current in the loop at just the right time so that the push always contributes to the rotation, not cancelling it out. So just like you keep the roundabout spinning by timing your pushes correctly, the commutator keeps the motor coil rotating continuously. Electric motors are everywhere. Ceiling fans, electric toothbrushes, car window motors, and maglev trains. Even small toys use the motor effect to spin wheels. Understanding this effect lets engineers design systems that convert electricity into motion efficiently, turning invisible forces into visible movement. So remember, the motor effect is all about forces on current-carrying wires in magnetic fields. Fleming's left-hand rule helps predict direction. The force depends on current, wire length, and field strength, and in loops these forces produce rotation, the principle behind every electric motor. Simply speaking, we're using an electromagnet to repel a permanent magnet. Invisible pushes, visible motion. That's another GCSE Science Simplified.